Good morning. I want to look at two situations here that use applications of similar triangles, and they're both very popular situations that you'll see. They really both have to do with a lot of physics and science principles. But the first one's going to be using shadows. Shadows define heights, and we're going to indirectly find the height of a very, very tall object based off of similar triangles. The first thing we need to recognize is that shadows are created, of course, by the sun. The sun is 93 million miles away. So in this situation, the sun would be way up here, but again, 93 million miles away. All right? And because it's so far away from us, and because these two objects are so close together, there's realistically no difference between the rays of the sun. So that gives us that the lines, the rays of the sun, we can consider them to be parallel lines. Now, because they're parallel lines, let's go ahead and draw that in and see if this makes a little bit more sense. Because they're parallel lines, we can see that this line and this line, these are rays of the sun, are parallel. I know my drawing's not very pretty, but they are parallel. Further, the ground creates a transversal. And hopefully you can see now, because I have two parallel lines and a transversal, that right here and right here I have corresponding angles. And we know corresponding angles are congruent. So I have two angles that are congruent to each other. Now, in order to be similar triangles, you know we need at least two angles to be congruent, two different pairs of angles, I should say. So I need one other pair of angles, and that's where we're going to go with the clock tower and the stick. 99 times out of 100, we're going to assume that the clock tower was erected correctly and is square to the ground, so that's going to be a 90-degree angle. And we're going to assume that the stick is also a 90-degree angle. Okay? So now we have two angles. So we have angle-angle similarity, and because we have angle-angle similarity, we have similar triangles. That's really all I needed to know. All of that can happen in my head very, very quickly just to recognize that I have similar triangles. And now it just becomes a matching game, and you want to match up corresponding parts. So it tells me in the directions that the length of the stick is a 3, and that the length of the stick's shadow is a 1.5. Further, it tells me the length of the building shadow is an 8. And of course, I'm left to figure out the height of the building, or the clock tower in this situation. So at that point, I'm going to match corresponding parts. So the x, the height of the tower, is going to correspond to the height of the stick. So that's going to be x over 3. And that has to be proportional to the same relationship with the shadow. So the shadow of the tower and the shadow of the stick. So 8 over 1.5. At that point, I have some algebra. I'm going to cross multiply and solve. So I've got 1.5x equals 24. And when I divide both sides by 1.5, I get that x has to be 16. So I've found the height of the clock tower as being 16. Okay, our second situation of using similar triangles is also based off of physics principle. This time we're going to use mirrors or some sort of reflection to indirectly find the height of something else that's super tall, and it's not really something that you can measure. So right here at the bottom is where it's talking to us. It says these angles are congruent because the light reflects. What they're talking about here is a physics principle that says that the angle in which something moves into an object, into a reflection, is called the angle of incidence, is always going to be equal. It's always going to bounce in the same exact angle. It's going to be the angle of reflection. So that's a physics principle for you, that the angle of incidence is equal to the angle of reflection. And that's true for a pool ball. If you think about shooting pool, the ball bounces off the rail in that same angle. It's the same for a bounce pass in basketball. If you bounce the ball here, it's going to bounce up at the same exact angle. And because of that, that gives us that these angles are congruent, because the light reflects off the mirror in the same way. Now, it's super tempting to look at this and think that those are vertical, but please recognize these are not vertical angles. In order to be vertical, so these two would be vertical, but not this one. But that's okay, because we still have them congruent, and that'll work for us. So at this point, I really just need to label parts. Now that I have congruent, well, same thing as above, actually, sorry. We're going to assume that all heights are at 90 degrees, and you can see now that I have two angles, so I have angle similarity. Now you're going to measure and see the height of the ground to Jim's eyes is 150 centimeters. The distance from the middle of the mirror to Jim's feet is 100. The distance from the middle of the mirror to a point underneath the traffic light is 450, and clearly we're looking for the height of the traffic light. So when I match up corresponding sides, the height of the traffic light and the height of Jim must be corresponding, x over 150, and that must be proportional to the height, the distance from the traffic light to the mirror and the traffic light to Jim. At that point, it's a cross multiply and a solve, and you get 100x equals 67,500, and when you divide, x has to be 675, and we're in centimeters.